Hi everyone. In this video we're going to continue our work on truth tables, which is a core aspect of propositional logic. So in the last video I introduced you into the basics of how to set up a propositional argument, a propositional sentence on the truth table, and showed you how to build the reference columns to the left so that we can plug in the values for a complete statement on the right. So we're going to pick up the thread on that a little bit here. I think the most important thing to bear in mind when building the truth tables is that practice and repetition is really the only way to pick up the skill and learn how to discover the values for our operators. So we're just going to continue along that path here in this video and then work up towards being able to fill in a complete truth table for an argument to test that argument for validity. So let's work on writing a truth table for this sentence. This sentence reads, if R, then either S or not P. Okay, so you might just have a quick look at the sentence before attempting to write a truth table for it. We have three different connectives, as I see it. We have our horseshoe, our conditional. We have a disjunction, and we have a negation. And the disjunction is bringing together either S or not P, right? And this is set off in parenthesis. And then we have the antecedent being set off by this entire parenthesis. So this entire parenthesis is the consequent. So the first thing we have to do when building the truth table is figure out what the scope of it is. In other words, how many lines do we need on our reference table? So as you may recall from the last video, the key to doing this is to follow our formula. L equals 2 raised to n, where n equals the number of variables in the statement. Because this statement has three variables, R, S, and P, we're going to raise 2 to the power of 3, and so therefore L equals 8. So we need 8 total lines on the reference table, 8 lines to complete the table. So our reference table is going to look like this. I've just written it out here for you on the left, and let's just have a look at it here before filling out the table. This is how you will complete the reference table for any complex statement of 3 variables. We need 4 values of true, 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 and then 4 values of false. And then we are splitting, I like to think of it as we split those values in half for the second column, where we have 2 rows of true, 2 rows of false, 2 rows of true, 2 rows of false for S. And then we will split these values again such that in the third row we're alternating true, false, true, false, true, false, true, false for the third variable. So we're bringing it down first 4 and 4, 2 and 2, 1 and 1. For any 3 variable complex statement, the reference tables will always look like this. So we're always beginning our reference tables with true values. Okay, that's a very common mistake students make, is to begin perhaps the last one with a false value. No, that should never be, it should always be true. And so what this is doing is essentially setting up the every possible combination of truth functionality for 3 variables. Okay, so these are going to be sort of the our guiding compass, as it were, as we plug in the values for the statement. So now let's have a look at the statement. Remember that when we're building truth tables, we have to bear in mind what the goal is. In other words, what is the truth value we're ultimately trying to shoot for. And in any complex statement, the goal, the final thing we're looking for is the main operator. The truth values for the main operator are the determining values of the whole sentence. So we have to think for a moment about what that main operator is. And as I see it, the connective that appears after outside of the parenthesis is the horseshoe. So this is a conditional. The conditional is our main operator. So this is our goal, right? Goal. This is what we're really shooting for in breaking down the truth table, plugging in the values for every other operator. Now, as I discussed in the last video, we can't begin with our goal, unfortunately. Truth tables sort of force us to begin with the simplest part of the sentence and build our way out to that goal, because in a way, the values of the main operator are they're impacted by the values of every other operator in the sentence. So we have to work with the simplest parts of the sentence first and then build out to the operator. So my order of operations, the one I like, is to plug in the values of R first. Let's take care of that antecedent first. You could begin in parentheses first and try to discover the values of the wedge first. But I like to knock out this standalone antecedent, as it were, so that we can then work inside parentheses. So in order to discover the values of R, I simply have only to look over to our reference columns and plug in the values as they appear in those reference columns. We're not affecting them at all because R it is not negated or anything like that. It is simply the antecedent to this conditional. So if we look for row 1, we see that the value is true. So I am going to write a true here, a T for true. And then for the second row, I look over and I see it is true on the second row, another T. And then on the third row, I see over here that it is true again. And on the fourth row, R is true. Okay, 4 rows of true. If we proceed down on the reference table, I see that the 5th row is false. And 6th row I see is false. And the 7th row is also false. And the 8th row is false. So I encourage you to write this along with me as you're watching. A couple of things to bear in mind as we're writing out the truth table. These can get kind of sloppy, and if they get sloppy when you're writing them, it can become easier to make a mistake because, as you can imagine, a lot of the values of the connectives are contingent upon the values of the variables. And if we end up sort of confusing which value is appearing in which row, you can easily make a mistake. So some students like to use graph paper or at least line paper as they're writing this out, and I do kind of recommend that so that you can hold on to the values of each row in the proper place. Okay, so these are the values of our antecedent R. Now let's work on what is appearing in the disjunction. So in the disjunction, we have a disjunction of S and not P, right? The disjuncts are S. I'm going to write disjunct 1 here for S, so we're clear. And disjunct 2 is not P. The negation of P is disjunct 2. So we have to find the values of wedge by bringing them into the truth function rule for wedge with S, the values of S and P. So let's begin by plugging in the values of our first disjunct, S. So in order to find S, we look over to our reference columns, and I see that the first row for S is true. And then for the second row, I look over again, and I see that the value is also true. And then I look to the third row, and I see that S is false in the third row. And then I look to the fourth row, and I see that S is false. And then moving on to the fifth row, I see that S is true. And then the sixth row, I see S is true again. because we're alternating in 2s. And then in the 7th row, I see S is false. And finally, I see in the 8th row that S is false again. Okay, so these are the complete values for S for our first disjunct. And just kind of take a moment for yourself and make sure you've copied this out accurately. And also make sure that the number of rows is arranged correctly, 8 rows, right? With 2 values for true, 2 values for false, alternating throughout S. Okay, so let's think for a moment about what we have to do next. Disjunction is bringing together the disjuncts S and not P. So how are we going to find the value for not P? Well, not P just simply takes the values for P as they appear on the reference table and negates them, right? So whatever the values are for P, we flip them, right? We turn them into their opposite. So not P, the first row, I look over and I see that the first value for P is true. So not P is going to be false, right? False. We just take the opposite value every time. On the second row, I see that P is false. So not P is true. And then on the third row, I see that P is true. So not P is false. And then on the fourth row, I see P is false, so not P is true. All right. We move along to the sixth row. I see P is true, so not P is false. And then the seventh row, 1, 2, 3, 4, 5, 6th row. I see P is false, so not P is true. And then the 7th row, I see that P is true, so not P is going to be false. And then on the 8th row, I see P is false, so not P is true. Okay, so we have these sort of inverted values for P under not P, alternating the values. False, true, false, true, false, true, false, true. Okay, good. Take a moment and make sure you've kind of recorded this accurately. These are essentially the values of the disjunct, first disjunct and second disjunct, and now we have to think about the values for wedge itself. Okay, so in order to complete the statement that's in parentheses, we gotta remember our rule for disjunctions. When are disjunctions true and when are they false? Our truth functionality rule tells us that wedge is true as long as one of the disjuncts is true. You only need one true disjunct in that either or sentence for wedge as a whole to be true, to have a true value. If, however, both of the disjuncts are false, then the disjunction as a whole has a false value. So wedge is only false when both D1 and D2 are false, right? So let's compare the values of the first disjunction to the second disjunction and draw in the values for wedge. Okay, on the first row, I see that S is true and not P is false. Well, because we have this true value here under S, we know that the disjunction in the first row is true. On the second row, I see a true S and a true not P. So both of the values for the disjunction are true. So wedge as a whole is true. We then have in the third row a false S and a false not P. So the values for disjunction as a whole, in this case, on the third row, has to be false, right? We have two false disjuncts. Both of them are false. Disjunction as a whole is false. Okay, moving along, I have a false S and a true not P. Because I have this true not P, I have one true disjunct. So disjunction as a whole is true on the fourth row. On the fifth row, I have a true S and a false not P. So because I have this true S, disjunction as a whole is true again. Okay. And then on the 6th row, I see a true S and a true not P. So disjunction as a whole on this row is true. On the 7th row, I see a false S and a false not P. So because both of the disjuncts are false, the wedge as a whole is false. 7th row of wedge is false. On the 8th row, I have a false S and a true not P. So because I have a true not P, disjunction as a whole is true on the 8th row. Okay? So I have the values of wedge in blue here. They are true, true, false, true, 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 false, true. Make sure you've written that out accurately. Make sure we have them sort of, I like to use different colors here just so you can sort of organize how the disjunction is sort of the most important connective within parenthesis, and it's bringing together these values for S and not P. All right. So, last but not least, we have to find the values for our main operator, which is our goal, conditional. So in order to do that, we have to think for a moment about what is actually, what the conditional is a conditional of. What is the if-then bringing together in terms of its antecedents and its consequence? The antecedent, the first part of the horseshoe, is this R statement, right? The values of R are the antecedent. Whoops, this is sloppy. Apologies. And then we have to think for a moment about what the consequent of the horseshoe is. We have S, wedge, and not P. Remember that with these complex statements, the part in parenthesis is actually the most important connective, because that is governing the total values, or it sort of has as its scope all of the other values within parenthesis. So wedge is actually the consequent. We are bringing together R and wedge with conditional. So the values for wedge are the consequent, not S and not P. Be very careful with that. This can totally set off the values of horseshoe, as you can see, if we pick another one of the variables. This is the consequent. So we are sort of bringing together under horseshoe the values of R and wedge. So in order to do that, we have to remember for a moment what the truth functional rule is for conditional. The horseshoe is going to only be false under one scenario, and that's where we have a true antecedent and a false consequent, because that's really the technical violation of validity. Every other combination of values is true. So if we have a true antecedent and a true consequent, horseshoe as a whole is true. If we have a false antecedent and a true consequent, horseshoe is true. If we have a false antecedent and a false consequent, horseshoe is true. So the only scenario where horseshoe is going to be false is where we have a true antecedent and a false consequent. So let's plug in the values for horseshoe and see what this ends up looking like. So on the first row, our antecedent's value is true under R here, and our consequence value is true. So based on our rule, we know that on the first row, the value under horseshoe is also true. Okay. On the second row, R is also true. The antecedent is true, and the consequent is once again true. So horseshoe on the second row is also true. All right. Moving on to the third row, I see that R is true, the antecedent is true. Aha, but I see under wedge that the consequent is false. So horseshoe as a whole on the third row has to be false, because we have a true antecedent and a false consequent. That is our technical definition of invalidity. We then have on the fourth row, we don't stop there, by the way, when we're doing a complete truth table, we keep plugging in these values. We have a true value under R, so our antecedent is true, and I see a true value under wedge, so our consequent is true. So the fourth row for horseshoe is true. Moving on, for the fifth row, we have a false antecedent under R and a true consequent, so horseshoe as a whole is true. Remember, this can be a little tricky. You can have a false antecedent and a true consequent, and the horseshoe as a whole is true. It's just the reverse, true antecedent and false consequent, that takes a false value. Okay, moving on to the sixth row. R is false, the antecedent is false, and I see that the consequent is true under wedge. So horseshoe, the conditional as a whole, is true on the sixth row. On the seventh row, I see that R is false, the antecedent, and the consequent is false. So horseshoe, we know as a whole is true. You can have those two parts of the conditional be false, and the conditional as a whole is true. This is a peculiarity of the conditional that you just have to get used to, right? And finally, on the eighth row, we have a false antecedent and a true consequent. So horseshoe, once again, on the last row is true. Okay, so as it appears here on the table, horseshoe, the conditional is only false on the third row, where we have a true antecedent R and a false consequent under wedge. So just in order to sort of label these values, we are going to put a box around them, just to sort of create a visual guideline that these are the main operator values, and therefore they are the most important values of the whole sentence. Okay. So this is a complete truth table for a three-variable complex statement that has a main operator outside of parentheses and also within the scope a disjunction and a negation. All right. So make sure you've written this all out before moving on, and we will continue along here. Now let's have a look at how to build truth tables for arguments. So far we have just been building truth tables for sentences that aren't advancing an argument. Now we're going to plug in the same principles essentially in order to determine the validity of an argument using our rule for validity. So recall that valid arguments are arguments where if we have true premises, it's impossible for a conclusion to be false. So in other words, we're just going to be essentially plugging in that technical definition of validity to see if larger instances of complex sentences, when arranged as premises and a conclusion, have true values in the premise section and a false conclusion. So truth tables allow us to see invalid arguments immediately. That's what's really cool about this. We don't have to worry about content at all. All we have to do is discover through the truth functional rules of the operators whether or not arguments are unfolding with true premises and a false conclusion. And if they're not doing so, then we know that the argument's its formal structure is valid. But if it is doing so, if there are true premises and a false conclusion, we know the argument can't possibly be valid, regardless of the content. So here's how we write this. To symbolize a conclusion, or the therefore part of an argument, we just use a backslash to set it apart from the premises. Okay, so here's an example. If I have a premise like this, it is not the case that both P and Q, and then I have another premise P, therefore Q. So the conclusion sets off Q with that backslash. So that's just going to be our notation so that we're super clear about which parts of the argument are premises and which ones are conclusion, because it'll be very easy to make mistakes about determining the validity of the argument if we're not even sure which part of the notation on the table is the conclusion or not. So Q represents the conclusion just as a standalone variable. So let's try to determine the validity of the argument by building a truth table out. Okay, so here's how you would do this. Just try to copy this. We have on the left, again, our truth tables. And remember that, our reference tables. So the reference tables are set off to the left here, right? And in order to determine the number of lines we needed to build the truth table, we just plugged in our formula, L equals 2 raised to n. And because there were only two variables, P and Q, we knew that it was 2 raised to 2 or 4. So we needed 4 lines. And to build out that table, we had split the values of P in 2 rows for true, 2 rows for false. And then for Q, we split that in half so that we have alternating values of true, false, true, and false. Okay? So in order to build out the truth table for the argument, we are going to proceed from left to right with premises being partitioned off with these columns so that we're clearly differentiating the parts, the independent premises. So the first premise reads, it is not the case that both P and Q. Okay, that's premise 1. And then we have as premise 2 just P by itself. And so this has its own column. And then we have our conclusion marked with the \Q. Okay, so in order to determine the validity of this argument, we have to find the values for each premise and then the conclusion and see if it withstands the analysis of our definition for validity. So let's work on this by filling in first the values for premise 1. It is not the case that both P and Q. So in order to find this, we have to find the values of dot, right? And then we have to negate those values. Remember that the negation is a negation of dot. It is not a negation of P. It's not a negation of Q. It's a negation of the conjunction. So in order to find the values of dot, we have to conjoin the values of P and Q. So let's try to recall what the truth functional rule is for conjunction. If you remember, the rule for conjunction is that conjunctions are true only when both of the conjuncts are true. So we need 2 true values for dot as a whole to be true. As soon as there is one false conjunction, as soon as there is one false conjunct, dot as a whole is false. So let's have a look. On the first row, I have a true value for P, the first conjunct, and a true value for Q as the second conjunct. So on the first row, dot is true. Dot is true. On the second row, I go over to my reference column, and I see that the first conjunction under P is true, but the second row under Q is false. So dot as a whole on the second row is false. Okay? On the third row, I go over to P, and I see that P is false, and I see that the second conjunct for Q is true. So because I have this one false value, dot as a whole on the third row has to be false. Now in the fourth row, I see 2 false values for P and Q, so I know that the conjunction on the fourth row is false. So the values for dot within parentheses are true, false, false, false. Now we have to find the values for tilde, for the negation. So we are just, in order to do that, we are going to be negating the values of dot. So that's pretty straightforward. We just invert these values. Whatever these values are, the negation will be the opposite. So the first value for conjunction is true, so the negation is false. On the second row, the value for the conjunction is false. So the second row for tilde is going to be true. On the third row, the conjunction is false. So negation is going to be true. And then the last row is false for dot. So we have another true value for tilde. False, true, true, true are the values of this premise. Remember, these really are the values of the premise taken in its entirety. This is the full scope of the premise. False, true, true, and true. Okay, so that's premise 1. We've got that truth table written. Now let's move to premise 2. Premise 2 is just P. So all we have to do to find P is plug in the values of P on our truth table. There's no connective or operator here to consider. It's just an independent variable. So we just plug in the values for P. I see that P on the first row is true. And then I see that P on the second row is true. And then I see that P on the third row is false. And I see that P is false on the fourth row. Okay? So P is true, true, false, and false. Now let's find the values for our conclusion, which is Q. Q is, again, just a standalone variable, so all we have to do is plug in the variables for Q on the reference tables. So on the first row, Q is true. On the second row, Q is false. On the third row, Q is true. And on the fourth row, Q is false. Okay. So now we have the truth table written, and now we just have to apply our rule for validity to see if it's valid or invalid. So in order to do that, we are just going to cross-check the values of our premises to see whether or not we have an instance where there are true premises and a false conclusion. As soon as we see one case where there are true premises and a false conclusion, we know the argument as a whole is invalid. If it passes through on each row that criterion, we know that the argument is actually valid. It succeeds formally. So let's have a look. The first premise is false. The second premise is true, and the conclusion is true. Now, even though we have a false premise here in the first row, this actually checks out. This does not violate our definition of validity, because this is not a case where we have true premises and a false conclusion. So the first row is actually valid. So I'm going to check off the first row to indicate that it's valid. On the second row, I see that the first premise is true, and then I see that the second premise is true, and then, whoops, I see that the conclusion is false. This is a classic instance of a violation of validity. We have true premises and a false conclusion. So this is invalid. As soon as we have one case where the values are invalid, we know that the argument as a whole is invalid. I have to go no further in determining that. As soon as this appears, I know for sure that as a formal deductive argument, this argument does not work. A law of validity has been violated. Okay? Now we could go along and plug in the values and just check just for the sake of our own edification, I suppose. This one's true, this one's false, this one's true. So this row actually checks out. And then on the fourth row, the premise is true, the second premise is false, and the conclusion is false. So the fourth row is valid. But the argument as a whole is invalid because of the values that show up on that second row. Okay? So that's how we do it. That is how we test the validity of arguments with truth tables. So this is just essentially breaking down what I just showed you. Follow the order of operations and the main logical operator procedures check for lines with true premises and a false conclusion. That is the dead giveaway for an invalid argument. And you can see once again here, this breaks it down in a way that's a little bit cleaner. We have true premises and a false conclusion. So this is where the invalidity comes in. All right. So this is pretty cool. You're able to identify right away whether or not an argument is valid or invalid once we have a complete truth table, completely independent of content. This is just pure formal structure and the logic of the connectives, the logic of the operators, bringing together simpler parts of statements into complex statements. Okay, make sure you've written this down before moving along. And once again, practice makes perfect. Repeating these things is how you really pick up the skill and learn how to memorize the rules for our operators and therefore for testing validity as a whole. So let's do a little practice. Let's say we have an argument like this. I have the argument up here in blue, broken down into premises. The first premise says either either not R or S, not S, therefore not R. So this is the first premise. Either not R or S. This is our second premise, not S. And this is our conclusion, right? Not R, with the backdash. So try to build this complete truth table. The first thing you need to do is determine the number of lines we need in the truth table with our formula, right? So L equals 2 raised, in this case, to 2, because there are two variables, so L equals 4. So we need 4 rows on the reference tables. Build out the reference tables here, and complete the whole argument testing for validity. When you've done with this, you can move on to the next video.